our next speaker is Dr. Chantal Mustoe. Chantal is a research fellow in the CMAC Future Manufacturing Research Hub here at the University of Strathclyde, and she's going to tell us about some of her work on an autonomous data factory for the small batch cooling crystallization of active pharmaceutical ingredients.
This seems to be working. All right, so let's go ahead and get started. So Cameron talked yesterday about the QBDD framework and how we're developing, there's new and existing digital models in development that underpin this QBDD framework. But in order to develop predictive models, we need data to feed into them to both validate and train them and continue their developments. So the data, as Alastair said earlier, is coming from these 5 different data factories where we're making the most of an opportunity to collect structured, fair data, but also get the negative results that we heard about in the CCDC talk yesterday that are missing in current data sets. So what I'll talk about today is the crystallization screening data factory. And but you'll see the crystallization scale up at stage 1 of the lab tours. You heard about the amorphous solid screening from Michael yesterday, and you'll hear about it a little bit more in this section. And the microscale dosage form from DM squared, and the biorelevant dissolution from Hannah's flash talk yesterday as well. So what's the crystallization screening data factory? So this is a high-throughput, small-scale screening of crystallization across a wide range of API and solvent chemical space. So we ask our models, what experiment should we be running next? And this tells the robot what it needs to set up. So it gives an empty vial to our solid-liquid dosing robot, which then, once that's dosed out, it can be transferred into our crystallines, where we're collecting a rich data collection of image analysis, transmissivity, to give us information about particle shape, size, nucleation, and growth kinetics. So once that's finished, the robot can then remove it. We'll take that image analysis, extract those parameters that I was talking about, feed that into the database, and back into our models. But it's always more exciting to see these things in action, so let's watch a video of this integration happening. Oh, I should also say we use our Bayesian optimization models, which allow us to target areas of high uncertainty in our models, but onto the video. So that's our data factory so far. We showed some smart prediction models for the solubility experiments in there. And as I mentioned, we are using Bayesian optimization to optimize nucleation and growth parameters and particle aspect ratio as well. But we're looking to generate a database that's machine learning ready for a crystallization classification system. So we're part of the way there because all this information is necessary, but we also want to look at information to do with physical form, fouling, aggregation, and to do that we need to start isolating and adding more stations to our data factory. So what we see here is we've been working with Glasgow School of Art to set up some new lab configurations, test out an early model of a filtration system up there, because we need these all these different data types to feed into that crystallization classification system so we can continue to develop existing models and also make new ones that say, so we have this toolbox where we can say, here's an API, how should I crystallize it? So how this is fitting, I went through this workflow earlier, and these new stations, planned stations, come in with, we start out with Raman spectroscopy and optical assessment. Again, that's to look at physical form, yield, look at fouling and aggregation, and particle size by an inverted microscope. Then that's handed over to the robotic filtration station where we isolate the powder, and that is going to be fed along to XRPD analysis in the Endeavour. So this is all yet to come, so to feed into our crystallization classification system, so something to look forward to. And we're also looking to scale up our current capacity. So I mentioned we're doing, the video mentioned we're doing 15,000 experiments a year, or this is what our current potential is. Each of these experiments has 5 crystallizations or 5 cycles opportunities for crystallization. So if we scale this up by 2, that would bring us to 150,000 crystallizations a year. So we are talking about high throughput data here. And each of those experiments has hundreds of images to give us all those nucleation parameters, and then start adding in the physical form and fouling and aggregation, and you have a database that can underpin a crystallization classification system. So finally, it's important to facilitate the human-robotic or autonomous platform interface. And in order to do that, again, we're working with Glasgow School of Art to create augmented reality where we can easily see where our samples are at any one time, and maybe highlight that a particular instrument is in need of maintenance or our solvent library might be filled. So this is quite exciting as well, because this is a collaborative lab environment where robots and researchers work in harmony. And with that, I want to thank many people who are involved in this, and hand over for questions.
Thank
you. Once again, good presentation, just like the last time I saw. Nice update as well. Kevin Gerard from Pfizer. Question about what data are you storing in the end? So, you obviously 15,000 now to be 150,000 experiments times, thousands of images per experiment. That can be a lot. So I guess what I'm wondering is, how are you storing it, and what are you storing?
Absolutely. So currently we're storing every single image and every single annotated image, as well as spreadsheets that contain the information we've extracted from those images. But the spreadsheets are relatively little memory usage by comparison. But we're looking into ways, because we'll have a lot of images that are white or black, and are giving us very little information. So we're looking into ways to delete the unneeded images to make our data storage more efficient.
I'll ask a quick question. So obviously, are there any sort of manipulations that are, like, obviously, like we do lots of things in the labs, are there any manipulations that sort of, it would be difficult to get a robot to do? And I'm just thinking as well, it's maybe a long time since I've been in a lab, I have to admit, but you know, when you're doing manipulations and you look at it and you might give the sort of the vial a little tap or a shake sort of thing, obviously a robot doesn't. So I'm just interested in that aspect and how, sort of what a robot can and can't do and the interaction with the human.
Absolutely. So there's things robots are particularly bad at, like picking up paper or picking up fabric. So picking up a piece of filter paper is a huge challenge. So we can work ways around this. We can look at the robot can do some of the manipulations, and we could couple it with image analysis to see whether or not it was successful at, like, if we knocked the vial gently against something, did it knock the powder back into the vial as we were expecting? Yeah. So it's going to take some model development to explore that, particularly any two-handed task. Do we redesign it, or do we get a two-armed robot? So,
brilliant.
So exciting, but we'll explore it.
That's really interesting, thank you. Does anyone else have any questions for Chantal? If not, I think...
Hi.
Sorry.
Helen Wheatcroft, AstraZeneca. So just a quick question. So how are you extracting the kinetic parameters from the huge volume of data that you're collecting?
Absolutely. So Chris and Paul are both developing image analysis on this. Chris has a showcase in the next session, which I highly recommend, so you can learn more about how he's doing that. And it is in real time. So say we might see that something's crystallized, we could stop cooling it down and start heating it up for the next cycle. So his image analysis is going to allow us to, again, optimize our experiments even further and continue reducing our energy waste. And if anyone has any more questions, posters 10 through 13 are all the DataFactory posters, and we've got a showcase, and we'll be in the lab tours as well.
Brilliant. Okay. Thank you very much, Chantal. That was good.